So here in chapter 17, we're going to be moving on to a little bit different topic. We introduced this topic in the form of redox reactions in the last semester, and we're revisiting how we can utilize those redox reactions to sort of capture the flow of electrons to do some work for us, looking at electrochemistry here. And so let's get some terms cleared up here. So if we talk about electrochemistry, this is simply just an area of chemistry that's concerned with the interconversion of chemical and electrical energy. If we're talking about galvanic or voltaic cells, then we're talking about spontaneous chemical reactions that generate an electric current. This is all of our batteries are galvanic cells. Now, in an electrolytic cell, you're driving a non-spontaneous reaction, so you're driving the current in the opposite direction that it naturally wants to go to make the reaction that you want to occur. So, for instance, I use this to take rust off of my cast iron pans, and you can use it for a whole host of different things. It's definitely how we generate almost all the aluminum that we have from alumina, which is aluminum oxide. So here we can see in a galvanic cell, or this isn't a galvanic cell, this is just the redox reaction of a zinc metal strip in a solution of copper sulfate. And the spontaneous direction of that reaction wants to basically, the copper wants the electrons more than the zinc is capable of hanging on to them. And so when that copper ion, the copper 2 plus, meets a zinc at the surface, it's going to snatch away those two electrons, and in turn it's going to precipitate out a solution as a solid, leaving that zinc 2 plus to go float away without its electrons. And that's the favored reaction. And so what you would see after some time is you'll just get this coloring or this coating of copper onto this zinc metal strip there. And what we'll be discussing a lot of in sort of this chapter is how we can sort of separate these things out so we can make those electrons have to flow through something in order to get to that spontaneous reaction, how we can utilize that sort of energy that's present. So let's take a look at the reaction we were just looking at and make sure that we are familiar with some of the at least labels we want to apply to things, what's being oxidized, reduced, and things of that nature. This is stuff that we've covered last semester, but we should touch on again just to make sure we're clear about everything here. So one useful mnemonic that I commonly teach students to remember what oxidation and what reduction is just oil rig. And if we can just remember those two words, then we can remember that oxidation is loss and reduction is gain. And so another common one that I've heard a lot is Leo the lion goes grr. So if you prefer that one, whatever helps you remember the definitions there. But if we're looking for what the oxidation half reaction and the reaction we show above with zinc and copper is, what is actually losing electrons? Well, the zinc is the one that is losing electrons, and we see that it goes from zinc to zinc 2 plus. So that indicates that this should be the oxidation half reaction that we'd see for that. For the reduction half reaction, we have a gain in electrons, and so for copper 2 plus, we are going from that to copper, so it must be gaining electrons, and so that half reaction just is copper 2 plus 2 electrons to go to copper. So if we're going to go label what the oxidizing agent is, then that is the element that's being reduced. By it accepting those electrons, it's helping oxidize something else, so it's facilitating an oxidation. And so that's why the thing that is being reduced is the oxidizing agent, and the thing that is being reduced here is the copper. And I should specify the copper 2 plus. And so that is our oxidizing agent here. If I ask you what is the reducing agent here, well, we have to look to what is being oxidized. That is the zinc solid. So the zinc solid is going to represent the reducing agent in this case. Okay, so and another just tip is I would say it's common in these problems to figure out to label what the oxidation, what the reduction, what the oxidizing agent, what the reducing agent is. So all four of those things are something that are frequently asked in particular questions. I would just say always go ahead and label what's being oxidized, what's being reduced, and then remember that label's flipped for the agent. So if something is being oxidized, it's the reducing agent. If something's being reduced, it's the oxidizing agent. If you're just consistent with how you approach that problem, a lot of times you won't flip things around, as can be easy to do when you're trying to keep it all straight in your head. So in this particular reaction, it says, what's the reduction half reaction for the overall cell reaction? And so reduction is gain again. And so what is gaining electrons? Well, if we look at the nickel, it's going from 2+ to a solid. And so it must be picking up electrons. If we look at the silver, then it is going from silver to silver plus. So each silver must be losing an electron. And so if we're looking for the reduction half reaction, I'm going to say it should involve the nickel 2+ to nickel, and we know that it takes 2 electrons in which to do that. So C would be the option we want to choose there. So let's look at the same reaction we've been looking at and see how we can arrange things so that we can extract some energy from this reaction. So if we set it up correctly, we can make sure that these electrons that are being they're going to be pushed through the circuit, which have some energy, are going to have to lose some of their energy to our circuit here. So we could have maybe a light bulb or something that's powered by the energy of those electrons moving in the spontaneous direction for this reaction. This is an effect of a galvanic cell. So the way that we're going to set up our galvanic cell is we're going to have on the left, we're going to have a solution, and on the right, we're going to have this solution. And on the left, we're going to put our zinc electrode in there, which is also our zinc metal. And on the right, we're going to put our copper electrode in there, which is just going to be our copper metal. We're going to connect this all through a wire. Now, if the electrons move from one to the other, they'll have to go through that light bulb, and they will be able to provide some power to that light bulb as a result. And in order to complete the circuit, this is probably one of the harder concepts some students have to understanding this material, is we're going to have to use this salt bridge. And the salt bridge is just something that is going to help us maintain a balance of electrical charge, because what I think a lot of people don't appreciate when they first look at these is, well, in this case, the zinc is going to be losing electrons. We can know that the electrons are going to come from the left. Well, if you're depleting all this negative charge over there, you just have this buildup of positive charge in that beaker to the left. And that is not going to be favorable at all. So what we need to do is, for every maybe 2 electrons, we've got to throw one of those sulfates in that solution over to the left, and the salt bridge helps us do that. It just moves the charge of usually these inert salts that are placed in this sort of gelatin that is inside the salt bridge, and it just allows those inert ions to move to one side or the other to replace either the depleted charge or the accumulated, or neutralize the accumulated charge that's growing in those particular areas. So on the other circuit, we see that we're going to be getting electrons, so we better add some potassium over to that side to equalize the charge, or just going to be building up tons of charge there. So it's necessary to complete the circuit to have this salt bridge. So we see the electrons going from the zinc, just as I mentioned, and we see them going into the copper electrode, and then we see the sulfate going still in a clockwise fashion through the salt bridge. And then when we get to the, if we were to focus more on the positive charge, we see that we have zinc 2+ leaving the electrode. We have potassium moving to the right. We have copper 2+ going up. So effectively, those are all moving in a counterclockwise fashion around that circuit. And so the positive moves in one direction, the negative moves in the other. Another confusing aspect of this is back when people decided the direction that they wanted to consider charge moving, they didn't know about electrons. J.J. Thomson hadn't come up with that yet. And so they didn't know what the charge carrier, what was predominantly the charge carrier in these circuits. So it was sensible to just say that that's the direction that the positive charge flows. So if you are talking about current, the current is actually moving in the opposite direction of the electrons. It really doesn't change how we treat these things mathematically or anything else. It's just a convention and it works just fine. There are, of course, some situations where we can say positive charge moves. That's often when we talk about semiconductors, but that's beyond us right here. So the salt bridge allows for completion of the electrical circuit. This is largely stuff I've just said, but it is important to reiterate and understand what this is doing. And it just contains this gel-rich and this inert salt. In this case, we're using the potassium sulfate. And again, it's just serving to sort of replace charge that's lost or to neutralize accumulated charge in a particular area. And because we've taken and separated these reactions or how this reaction occurs, we're able now to harness the electrical energy from these electrons moving through the circuit. Another important thing to point out is just we have, you'll hear again and again, an anode and cathode through this sort of discussion. When we're talking about galvanic cells, the oxidation always occurs at the anode, and we also give it a negative polarity at that anode. When we're talking about the cathode, that is where reduction is occurring, and that always gets a positive label. And so we'll go through this and reiterate some of this stuff in just a second here as we talk about anode and cathode. So again, at the anode, we're saying, well, this is where oxidation occurs and electrons are being produced. The anions are going to migrate towards the anode in order to replace that negative charge that's just been lost. And this is usually labeled as the negative electrode. For the cathode, that's where reduction occurs and the electrons are consumed. The cations are going to migrate towards this cathode. This is going to be labeled as a positive electrode. Okay, so let's review how we balance a redox reaction in an acid or base. This is something that we covered last semester, but it's been some time since you looked at it, so it would be good to go over it again. So we're going to look at balancing it in an acid, and here are the rules that we use to balance it. So the first is just to write the unbalanced net ionic equation. That's what you're seeing above here with the nickel going to nickel 2+, the dichromate going to chromium. And the second thing is decide which atoms are oxidized, which are reduced, and write the two unbalanced half reactions. It's not totally necessary to figure out which one's reduced and which are oxidized to balance the reaction. We can figure out those labels later if we need them. But it is important to split things up by the species. So if you have dichromate in a half reaction, you better have chromium on the other side, and nickel should be with the nickel as well. Okay. So then we're going to balance both half reactions for all atoms except oxygen and hydrogen. So what's presently there. And then we have to add water to balance the oxygens. And then now that leaves us an imbalance usually of the hydrogens, so we have to add H+ in order to get things balanced. And then we just have to balance the charge to make sure that the charge is conserved on both sides. Then we have to balance where we have to add both reactions, and since we can't have a net gain or net loss of electrons, we have to make sure that the number of electrons in one half reaction is equivalent to the other half reaction. And so sometimes we have to multiply one by a factor in order to get things to cancel out. And then we're going to just basically make sure that everything looks good by balancing both the atoms, making sure the atoms are balanced as well as the charge is balanced on both sides. You can have a net charge on the positive, on the reactants or product side. It's just got to be the same on both. And so we'll go through this process with this particular reaction. If you wanted to balance things in a base, just remember at the end of the reaction, you just neutralize all the H+. So if you had 7 H+, you're going to add 7 hydroxides to both sides, and then your reaction would be balanced in a base at that point. So like I said, we're looking at this nickel and the dichromate here. And so we've got that unbalanced reaction. We split these things into two pieces. So the nickel going to nickel 2 plus and the chromium going to chromium 3 plus. And so it says balance both half reactions for all atoms except oxygen and hydrogen. So that means I'm going to have to add a 2 here to the chromium in order to balance it. And so the nickel, I don't have to do anything because we have one on the reactant, one on the product side. So the next thing we have to do is balance each half reaction for oxygen. So nickel has none, so it's not of concern, but we have 7 oxygens on the dichromate. So I'm going to have to add 7 waters in order to give 7 oxygens on the right-hand side, since we have 7 on the left. Okay. So then that gives us 14 H's or hydrogens on the product side. We can't leave that unbalanced, so the H pluses are what we are, or the hydroniums are what we're going to use to balance out the H's. We had 14 to the left hand side there. So that moves us to the next part where we can balance each half reaction for charge. The nickel is neutral on the left hand side and it's got a 2 plus on the right hand side, so we need to add 2 electrons. And so if we added it to the left, we'd have a 2 minus on the left and a 2 plus on the right. That didn't work. If we add it to the right, though, we have a 2 plus and a 2 minus on the right. That's going to give us a neutral charge, which matches the charge on the reactant side. For the next one, we look at it, we have 14 plus and then 12 or 2 minus, so it's going to give us a 12 plus net charge. We have a 6 plus net charge on the right hand side. So basically we've got 6 more positive charges on the left hand side there. So we need to balance that with 6 electrons. Now we can't add those 2 reaction as is because then we would have basically 4 net electrons on the reactant side. And so we have to make sure that the electrons cancel out. So that means we have to multiply everything in the nickel reaction by 3. And so now we have 3 nickels to 3 nickel 2 plus 6 electrons. We're ready to add them now. And so we add these 2 balanced half reactions. The electrons cancel out. We're left with 14 H pluses reacting with dichromate plus 3 nickels to yield 3 nickel 2 pluses, 2 chromates, or not chromates, but chromium ions, and 7 waters. So we can check our answer to make sure things are balanced, but for the most part, this is what we're looking to do as long as we're balancing in an acid. We can look at the 12 plus charge on the left, and we got a 12 plus charge on the right. That's usually a pretty good indication you've done something right there. Okay, so for same galvanic cell, what electrode or which electrode is going to be our cathode? We know the nickel is what is oxidized, and we said that's where the anode is. So then I'd expect the dichromate in this case to be the cathode, or where the cathode is sitting at. And so that you'll notice here we're using an inert electron. So dichromate as well as Cr3 plus of the chromium cation, they're both aqueous and they're in solution. So we need something, some site at which these things can react. And so usually we use an inert conductor like platinum or carbon to serve as this inert electrode. And so that platinum is still where the reduction is occurring. And so it's still being where the electrons are arriving at, right? And so we give it a positive notation there as well. The anode, that is going to be where we have oxidation occurring, and the nickel we see is losing 2 electrons, so we know that's where the electrons are leaving. And if we said which directions are the electrons flowing, they're flowing from the anode to the cathode. And so we sort of always expect that in a galvanic cell. Remember, the current is actually going the opposite direction that we're showing the electron flow. Like I said, just mentioning the inert electrode, it's just going to be something when we have a non-metallic species. It's just going to be used as an electrode, and so that can be carbon, platinum. There's other materials, but this is what this is showing. And in this case, the reaction is occurring at that surface of that electrode on the platinum or carbon that we have there. So if you have a dichromate that's sitting in there and it's getting several electrons and it's reacting to go to Cr3 plus, and it's half reaction. So which of the following statements is correct here? We have electrons leave the cathode and travel towards the anode. We just said that it leaves the anode and goes towards the cathode, so I'm going to say that one's incorrect. In a galvanic sode, the cathode is negative. We've been showing the cathode is positive, okay, so that doesn't jive with what we had there before. C says the reduction occurs at the cathode. That agrees with what we've been saying, so I would say that's probably the correct answer. D is cations migrate towards the anode, and that's not going to be the case. They should migrate away from it. And so the electrons are produced at the cathode. That is also incorrect. The oxidation is occurring at the anode. So the reduction occurs at cathode is the correct response we're looking for there. So it's often nice to have some shorthand that can communicate a lot about that galvanic cell in a sort of condensed form. And so if we take this particular reaction of zinc being oxidized and copper being reduced, we look at all the overall cell reaction that we have there. One of the popular ways that we can rewrite this reaction in the shorthand form is we basically just write the oxidation that's occurring on the left-hand side and the reduction that's occurring on the right-hand side. The single bars that you see are indicate where we have a phase difference, so we're going from zinc solid to zinc aqueous. And then the double bars you see there are to indicate that we have a salt bridge present. And then we have the reduction on the right-hand side always, and that's copper going to copper solid. And so the anode is on the left, and we write basically what it starts with to what it's reacting to, and then the copper, what it starts with on the right-hand side to what it finally ends up as the copper solid, and that's at the cathode. And don't forget, those double bars represent the salt bridge that's present. The electron flow, if we're looking at this particular way this shorthand notation is written, is the electron flow goes from left to right. So just to make sure that we've touched base on some of the trickier notation, let's look at when you have an inert electrode. So for instance, when we look at something like iron reacting with 2 iron 3 pluses to form 3 iron 2 pluses, you can see in that right hand half reaction, so the right half of that cell where we have the reduction occurring, we're going from iron 3 plus to iron 2 plus, and both of those are aqueous in solution. And so where we're picking up those electrons, we need something inert there like the platinum electrode to convey those electrical charges or the electrons to that 3 plus and to yield us the 2 plus. And so how are we going to do the shorthand with this inert electrode present? So we're still going to have oxidation on the left-hand side, which should be the iron solid going to iron 2 plus. And so we write that. And we have one single bar between those two because they're in different phases. We put the double bar to indicate that we have a salt bridge present. And then we have iron 3 plus going to iron 2 plus, as the electrons are flowing from that 3 plus or flowing to the 3 plus, yielding 2 plus, and that's happening at the platinum electrode. So we denote that inert electrode at the very end there, and it also has another single bar between it indicating that it is in a different phase. So I don't have a pretty picture of this particular reaction for a galvanic cell, but copper reacting with chlorine, well, chlorine gas is not something you're going to be able to make an electrode with, or chloride is not going to be something we can make an electrode with. So we're going to have an inert electrode present for this particular redox reaction. And the shorthand that we would have for this is copper solid going to copper 2 plus. Again, the oxidation on the left-hand side. And then we have the salt bridge, and we have chlorine gas, and then we also have that going to chloride as it picks up electrons. And then we have one more indication that we have a inert electrode with the carbon sitting there on the very far right hand side. So you basically write what is oxidized on the left, you write double bars for the salt bridge, then you write what is reduced on the right hand side, making sure that you put a bar between anything that has different phases. If there's an inert electrode, it shows up on that far side. There are the possibilities that on the oxidation side or the left hand side is where we're actually seeing the inert electrode. In that case, you'd put the inert electrode first with the bar, and then you'd put whatever solution, ions that were in solution there. One more thing to note is that you can make this a little bit more complicated if you want, and so you can provide more detail. I know you might not want to make it more complicated, but you might want to be able to interpret a more complicated shorthand, and that usually is just accompanied by the concentrations of particular substances present. So this tells us that the copper 2+ was in a 1 molar, was at a concentration of 1 molar. The chlorine was at a pressure or partial pressure of 1 atmosphere, and the chloride was at a concentration of 1 molar. And so that's how we can just provide a little bit more detail sometimes in the shorthand notation. So if we're looking at the shorthand notation here, remember on the left-hand side, we want what is oxidized. And so if I'm looking at that reaction, it appears that the half reaction for oxidation is going to be the nickel. And if we look at this, the silver is going from silver plus to just silver, so it's picking up an electron, so that's what is reduced. So that tells me I want the nickel on the left-hand side. And then, so that's going to be nickel going to nickel 2+. Notice we put the bar in there for the phase. We have a salt bridge, so we put the double bars, and then we have silver plus, and it's being reduced and picking up an electron, so it's going to silver. So we could also ask you for the sort of reaction from a shorthand notation. And so if we're looking at this particular reaction, we see that lead is being oxidized to go to lead 2+. The bromine liquid is being reduced and it's picking up this electron to go to bromide in an aqueous solution. And since the liquid and the liquid bromine and the bromide are neither going to form suitable electrodes, we need to have an inert electrode for that reaction to occur at. So it happens at a platinum electrode that we have indicate there on the right hand side. So if we're looking to balance this, then it's just lead going to lead 2+ plus 2 electrons. If we're looking at the bromine, it's just 2 bromines plus 2 electrons to go to 2 bromides. Summing those up, we end up with the overall reaction of bromine liquid reacting with lead solid to form lead 2+ and bromide. So in this last reaction or last clicker question of this particular lecture, let's look at just a galvanic cell, and it gives you the 2 half reactions that are occurring. It gives us at the anode, we have copper going to copper 2+ and silver being reduced to silver solid. And so it asks you what's the shorthand notation for this cell, and we know that we always put the oxidation first, and so it's copper going to copper 2+. And these things should be separated by 1 line. There should be a double bar in between the oxidation and the reduction is going to give us silver plus aqueous to go to silver solid, and so those should be separated by a single line too, and that should be on the right hand side. The one that agrees with that for the shorthand notation for the cell is D, so that's what we should expect. So that's the first half of this chapter, or at least with what we're going to cover here.